kind of improvising because I'm a bit of in a different machine, so the setup is going to look a bit different. But I don't know for how long can I. It's probably just be 10 minutes. To be honest, I'm kind of like. I think I've done. I know I've done this many times, but like I think one of the things that will help me here maybe is if I use something like SymPy, to kind of like try to get my sort of make sure that I'm doing the things correctly, right? But then at the same time trying to justify things, so not just accepting the solution that SymPy gives me. I don't know if you can walk through a SymPy like solving process. I don't know. Hopefully, and to be honest, SymPy quantum stuff, like I think I checked, but then when I was doing quantum mechanics, the quantum computing stuff, but then this is obviously a bit more focused on the quantum mechanics, so I think it's actually good. I mean, we'll see. We will see. Operators and blah 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 blah. So, but there's also like quantum computation stuff, quantum functions, states, and operators. We'll see. Quantum mechanics. But what I'm gonna try to do is I at the same time want to try Replit, because I've always been it keeps popping up in my Twitter timeline, and I did give it a try once, but then I never came back to it, and then I'm maybe it's even worth paying for the $7 a month to get like the AI explainers and all the other stuff that they do. I don't know. I've never really used it before. I kind of sign up with my Google account, connected to GitHub and whatnot, but then I was not sure even whether they support Jupyter notebooks, but they do. And I don't know if let's just do a small test. I have no idea. It's the first time I'm really using these, other than like let's see where that goes. Cool. Okay, so that actually opens a workspace that looks like pretty similar to like what you'd expect from VS Code or something like that. It looks cool actually. Code editors, this way I run the code. This is to run the code. I guess that's specific because it's a Jupyter notebook, right? And this is the output. Files. Cool. Okay, but what is these? So read me. Okay, there's notebooks. Oh, okay, that's the actual notebook. Create Jupyter notebooks on Replit. In the shell, run generate password, enter the password for your Jupyter notebook, copy and create the password to a Replit secret with the name notebook password. Run the REPL, open the web view in a new tab. You cannot log in via the web view in the workspace. Log in with the password you entered in step 2. Ooh, okay. You're obviously gonna probably see my password and stuff. I have no idea. I don't know. So not in the console, but in the shell. Read the instructions. I can't copy paste or like generate password. So it's just a test, so really I don't really care much I think about this notebook password stuff. What does it do? Enter the password for your Jupyter notebook. Okay, now I have to enter the password. So test 1 2 3 4. And now what? Oh, what? Now with the password. I think it just I see some lag. Okay, so with the following contents, add a Replit secret called notebook password with the following contents. Copy. How do I add a secret? A Replit secret. So Replit secret. here, secrets, got it. Key. Notebook password, and then this whole thing here. Add new secret. Okay, got it. And so that's the secret. Okay. And now what? And now just run. Okay, so now runs the thing. And now what? Okay, so that starts the thing. Oh, so now that actually builds a web view. That's cool. Okay, now I put the password, which you all have seen. What? Oh, okay. Should have read that before. Open a new tab. I guess that's the button. Okay. Interesting. It's an interesting setup. I thought you'd actually have that Jupyter like that Jupyter Notebook view somewhat here, integrated like StrangeWorks does. SymPy test. Okay. If I open home, like, and then do I just see the project there? Okay, it says timeout. Oh, there you go. It's likely because of the streaming Twitch Studio, I think. And so, valid credentials? No. What? Yeah, maybe I've run that wrong because I added that weird thing. Like maybe I should just start. Notebook password. I'm using like test. Oh, I have caps lock on. Test 1, 2, 3, 4. Now it'll work. Awesome. Okay, so actually I have now here the environment. That's cool. Okay. And I guess I can just it feels cool. I mean, it's pretty intuitive, to be honest. The web view. I guess I can close the web view, but okay, so that's Jupyter. So how do I like, do I have SymPy in here? Like SymPy as SMP. I guess that comes with like a bunch of libraries, right? Isn't it called like SymPy, import SymPy? Am I doing something wrong? SymPy. From SymPy or import. Like, I think people use that, right? Import SymPy as SMP. Yeah. SymPy. That's correct. How do I? What if I just say NumPy? Maybe they just don't have it, or as NP. Is this there? Maybe, yeah, that seems to be there. So how do I install SymPy? Can I install SymPy just like that? I guess so. On a Replit Jupyter notebook. Ah, there you go. There's a specific one about these with Replit. So you can just do that? You can just install it like this, probably. So it's got SymPy, so I could actually use it. I'm just curious, like, is this thing just stays there, right? So the actual workspace stays there. So, oh, cool. Look, so actually I can see the stuff in the console here that's being installed. That's nice. So I can always go back to this project, I guess, and just run it, and then that will just run the thing. And so I will just permission denied. User option. Blah. On your shell, type pip install. Ah, okay, actually, interesting. So I can probably. So I actually have a full-fledged environment. So I can do pip install SymPy. Okay. And I should probably restart this, right? The kernel at least. It also failed. SymPy. Is it the same? It's the same thing. Because I'm using the so pip install SymPy didn't work because I'm getting a OS error, permission denied. Check the permissions. A user, like, is this just user? Is like user just gonna, like, that doesn't require me to input a user, but it's gonna tell, like, do this for this user probably, right? So maybe that's gonna work. Because then I could do and kind of give it a try, right? So I maybe just while this is running, because what? Because it's slow because of the whole, maybe it's working. Let's see. Hopefully it's working. I'm really surprised because it is actually pretty it actually goes pretty smooth despite the fact that I'm streaming with Twitch Studio, because when I use other stuff, like, it usually goes super slow. So okay, come on. But yeah, basically, because I'm kind of stuck here, right? So, and I'm like, I'm it's taken me so many broken steps to get there, like small steps where, you know, I tend to just read stuff, the solution, and I'm like, yeah, whatever, that's kind of, but then I'm like, I'm trying to force myself to understand what does this mean, right? And then like I keep getting stuck with the notation of like, on one hand, like what are things like that, right? Which is like, this is the typical just I'd say evolution. Like if I search for free particle wave function, that's kind of that's how the model, that's kind of how it's modeled, right? So you have that basically you just have these, which is, I guess what it's saying, to be honest, is that it's just a something that is, because it's a complex exponential of e. This is just something that it's basically circling around, right? I guess intuitively that's what it means. But then, like, I keep it's so difficult, like to keep your head around, like focused on, am I doing the math, but am I understanding what am I actually manipulating with these objects and stuff like this. And you know, and so this is the eigenfunction, okay, then this is just like, you know, that's just, I guess that's how you would take it as from a free particle perspective. Cool. So now you have, you know, now we have this situation here, right? So there's this assumption where it's like, assume that's your starting point. Now you can still do that, right? And then, but this E stuff, these things are just at the end of the day, then you realize this is just a relative phase, right? And these things cancel out when you do that. So that's kind of correct. It's like always, I have to engrave in my head whenever I see an exponent, a complex exponential, it's usually a relative phase or a global phase, whatever it is, right? Here's kind of a global phase, I'd say, yeah. And so, but then I don't even know how to interpret that, because that's literally like saying, well, of a wave function is just a global phase or something. But again, then these stuff up here is what was W? Is W the angular momentum? I think so. They don't define it here anywhere. Anyway, and so that's all good, and then I understand these, and then I know how they get there. And actually that's funny, because I came across, I tweeted this yesterday, I came across this solution, not solution, but this question in physics or math exchange, right? And they really explain these in a way that they're like, it's frequency, it's motion at the frequency, okay, oscillatory motion at the frequency. This is frequency, God. But anyway, it's like, you know, these things cancel, like the whole thing with the global phase cancels out, but then if there's relative phases, they don't necessarily cancel out, then you kind of have this example. And then they go and they do these, right? And that's kind of what caught my attention yesterday, because I'm like, okay, so what's that, right? So really that is actually, it's funny because it is in a way similar to that identity of the inner product, but they express it like that. So complex exponential and it's maybe a generalization of the inner product, right? But still, like, there's and maybe because they are real, because to be like, look, because if I go and I say, like, what is the, how do you decompose a e to the power of I with trigonometry? Like, there's a way to derive that. also Euler's formula. Yeah, there you go, exactly. And because so this is so, and this is probably a fucking generalization. Like I don't know. So for some reason there's this identity, right, where it's like the, and again I don't know if that means absolute, like real value, absolute value, whatever, times these. But then again, the I think we know as per the stuff in here that that we've got the eigenfunctions are real and isotropic. That's why we are dropping. And I guess that's why you're dropping, yeah, because what am I doing? So that's why you're dropping. So you see, this is the whole X thing, right? That's yeah, that's it. That's how you get there. So you're basically got this so much to unpack here. Like you have here, actually, instead of just the cosine, you just actually have e to the power of all that. Like you have these, right? These can be unpacked into this cosine as whatever, but then you basically what you're doing is you're basically actually getting rid of the complex component of it, so the sinus component. That's why you keep the cosinus of the angle difference, right? Because it's the relative phases that you're caring about. Look, I think that worked out. That's cool. If I restart the kernel, will that work? I don't know. So that's how you get there. That's how you get there. But what is that? Like I forgot. Like I'd like to find an explanation of these. That is why I said that explains a lot of the that was to tweet about. Yeah. So it's because the phase difference. This is the phase difference. Now I'm assuming that here this phase difference depends on x, right? Because this can be different and a specific x, but where the hell is that coming from? Good question. Well, for something, we've got here that they say that the energy difference is set to h bar W. God. So here what they're saying is, I understand this means that they just okay, so that means that is basically a way you're saying you want this to be real, I guess. No, also not. I don't know. God. Where is that coming from, right? So here they say, really, that the coefficients or wave functions depending on which picture have a rotating phase angle or have a rotating phase angle if phi 1 and 2 are energy eigenstates. This causes the phase difference to actually rotate at the energy difference, so that that squared thing, so the probability density squared, the probability density, will exhibit oscillatory motion at the frequency yeah, okay, so that is, this thing here is the identity that they just tell you here. So that's something that you should just know, but I don't know how I am supposed to know that. How am I supposed to know that it's just something I guess you have to know, that what the actual rotate, the phase difference. The phase difference, relative phases rotate at something that's proportional to the energy difference. I don't know what's the intuition there, but that's an interesting thing, right? And then the reduced Planck constant is there just because. So that makes these equality cool, but like I don't know. Yes, okay. I think I know, because I think that the thing is, once you have these guys here, and so you're gonna have this difference, and so you can set up this difference. But again, what the hell is the t doing here? Like, how do I get the t in here? This is what I don't know. Anyways, what I'm trying to do is I'm trying to understand how can I just work my way out like towards this one. I'm trying to see if SymPy in a way can help me. And then the biggest challenge is, how the heck do I get this sinus in here? That was the other challenge, right? But I think if I manage to get this exercise in at least under 20 hours, like I'd have a good understanding of like wave function manipulation and stuff like that. So it's good. But now it's telling me maybe I have to restart. So maybe let's just close that. Let me just stop this. I just have to start the whole thing. Yeah, of course. That's telling me this because it's restarting. And so once it gets there, I'll do that. Okay, and now let's see if that works now. So we'll open the notebook. So many things that we are unpacking here. I'm gonna try to make a bit of a summary of things like this. It's like how do I retain these things, right? So I have wave functions, eigenfunctions, and then there's always the relative phase there, because that's just sort of the most generic thing that you do. And then there's just, you kind of pick a model, if it's like free particle or not, that tells you maybe how do you write that wave function. And then the interesting thing comes into, this kind of stuff, right? So to kind of say that, like, this is what I think trapped me, right? It's like I have these inner product between two eigenfunctions, to be honest, right? These are not wave functions, these are just eigenfunctions. I have this inner product between eigenfunctions, which represent states, eigenstates. And so if the inner product of these eigenstates, then it's there, in a way you've got these where you kind of have that thing that rotates. So the relative phase that you get out of that is something that rotates, and it's proportional to the energy difference between these. Maybe this is how you put it, right? And that is maybe because what would the inner product intuitively represent? Does it represent these areas in space where the two-way functions kind of are valid? Cool, I think I actually have to go. Anyway, let me just see if that works. So I've opened that, and now if I do this, that still doesn't work. But I actually have SymPy, right? No, that doesn't work. Oh no, it's sorry, I'm such a noob. It's actually a library. Anyway, I'll figure it out. Once I get it set up, I'm gonna be really happy, because that's gonna make that journey even more fulfilling, to understand and learn all this kind of stuff. Because essentially, you don't want to learn to just manipulate things manually. You want to learn what kind of tooling is available out there, so you can make sure you're not making mistakes. Because some of these things are just super complicated from a like the equation level perspective, right? And having that tooling, like, and understanding sort of the steps conceptually, and what it means with the inner product, the integrals and stuff, that's good. But then to solve these things, or even simplify these expressions, it's complicated. So anyway, that was a quick one. I'm feeling like I'm moving a little bit forward, but I'm stuck. I'm like in that probably eight hours already into this just one single problem. Anyway, see you next time.